Hi everyone, thank you for coming. I have the honor of introducing David tonight, so let me tell you a little bit about him. David DiLaura received a degree in physics from Wayne State University, after which he worked for 10 years as an illuminating engineer. In 1981, he founded Lighting Technologies Incorporated in Boulder, Colorado, where he directed the development of Lumen Micro. He was appointed Associate Professor Adjunct of Architectural Engineering at University of Colorado and established its lighting educational program. In 2000, he became Professor and Associate Chair for Architectural Engineering. In 2007, he joined Acuity Brands Lighting as Principal Illuminating Engineer in its Innovation and Technology Group. David is an esteemed member of many lighting industry organizations and has published more than 40 technical papers. He authored A History of Lighting and Light. Let me bring that back. He authored A History of Light and Lighting, was founder-in-chief of the Journal of the IES, and was an editor of the new edition of the IES Handbook. With all that said, let me hand it over to David. We can't wait to hear your presentation tonight. Thank you.
Thank you, Jeff. I've got my mic on, so I want to make sure everyone can hear it.
Yeah.
David? How's that? Is that better? All right. Yeah. Some of you may have seen the CBS Monday Morning Let There Be LEDs, and they were at my living room filming for 8 hours. And they really do power you. Too, right? But they put on a big apron. Let me add my welcome. I know that we've got some competition tonight, but it's good of you to join us. And my job tonight is to try and let you know that there's something that we can learn from history. What does history have to do with the latest little thing in LEDs and twisted pairs and controls and the pressures of the market and the lunatics who are telling us that LEDs will burn for $100,000 and do everything that we want? What does history have to do with that? I hope I can convince you tonight that history has everything to do with it. If we look back carefully, we will learn about disruptive technologies. We think we're living in a unique age. In my work in lighting technology, history has shown us that that's not the case. So I hope tonight that we can learn about the future by studying yesterday. I want to talk about the disruptive technologies in the history of lighting, and I want to do that in a way that I think is useful for those of us in the lighting industry. And therefore, I hope we can understand tomorrow by studying yesterday. Now, history is a dangerous and tricky guide. You have to be very careful because it can be ambiguous. We can look at our own histories, we can look at the history of any nation, any political organization, and every time that you see a history lesson that says, "He who hesitates is lost," you can also find a history lesson that says, "Look before you leap." So which one do you do? That's the task. History lessons are uncertain, they're ambiguous, and they can fall on both sides of the fence. But I think, like Mark Twain said, history may not repeat itself, but it sure does rhyme. And that's what I hope I can convince you of tonight, that the history of lighting and its disruptive technologies actually does rhyme. History is contextual. When we look backward, we have to imagine what it was like to live in that time. Here is a replication of a sign that began appearing in hotels in this city after Edison began installing the electric lighting system. And it says, "Don't light it with a match. Just turn the key by the door and the light will come on." And that was, of course, because everyone was used to gaslight. And that's how you started gas lights, with a match. Well, if we look forward, it gets very difficult, if not impossible, to predict history. The Club of Rome, in their 1963 report, said that the Earth would be a burned out cinder by this time, right? Well, that's not the case. We managed to do things pretty good. Let's talk then about the great transitions in lighting. And I've got a capital G there, and I mean the very large transitions. All of these things are characterized by a change in the technology of delivering light. And it actually is also characterized by the very nature of light itself. Very interesting notion. I'll speak more about that a little bit later. Public perception of lighting has shifted with each of these large technology changes. There's been very, very large-scale economic shifts. Companies go, companies come, and companies go again. I want to talk about the great transitions in lighting. I'm going to list them here. The first one has to do with candles. Yes, we're going to actually talk about candles. Then we're going to talk about gas lighting. Notice the dates. Talk about the invention of kerosene. One of the biggest, greatest advances in lighting was the development of kerosene. I'm going to talk about gas mantle lighting, and finally, electric lighting. We're going to break electric lighting up into two sections. And lastly, because it was so disruptive, the development of the fluorescent lamp. Let's go back to one of the very earliest lighting technologies, candles. The earliest candle that we know of, that we would call a candle, can be found about 100 AD in Rome. But people had been making rush lights that you see here for a few thousand years. A rush is a weedy plant that grows by a river. You take out the pith, you soak it in animal fat, it burns. But people began to make candles. Here you see a candle factory in 18th century France. This particular candle factory made wax candles for the nobility and for the church. Here is a factory that made tallow candles. Tallow is basically the burning of a cow, basically. You render an animal, you collect its fat, and you mold it around the wick. Now you can imagine what something like that is when it burns. I have ordered tallow candles from England and had them in my house and burned them. That was a mistake, right? People would put herbs and leaves and berries to try and get away from the burnt animal scent. And then in 1823, the great industrial French chemist Michel Chevreul discovered stearine. Stearine is, at room temperature, a flaky, waxy substance. It's waxy, but it's not a wax. It's a chemical. And it turns out that if you make a candle from it, it burns without any odor, almost no smoke, and is very, very luminous. At almost the same time, Carl Reichenbach discovered paraffin. He used Greek to describe this chemical he discovered, paraffin, meaning little affinity, which means it's very stable. And for those of you that read Sherlock Holmes, his name has all of these ominous repercussions, right? Yes? Carl Reichenbach got together a company that began to make stearine and paraffin candles, and it utterly changed lighting. Here are the characteristics of this radical change in lighting. Chemistry, science, now has a say in lighting. Chemists were new people that came into the lighting industry. People that had never been associated with lighting before were now principal interests in the lighting technology. There's a radical increase in the quality of candles, and there was a considerable decrease in cost. Sounds like a winner, right? You make it better and you charge less. Who's going to argue with that? Right? And of course, there's always a tax, and that tax is all the people that made tallow disappeared. No one wanted tallow candles anymore. It became possible to buy stearine and paraffin candles. Gas lighting arose in England in the 1830s, and there was some early work by Le Baron from France, and principally the French fellow Frederick Winslow, sounds German, but he was actually French, and Karl Kuhn in England, discovered that you could take things like coal and wood, and if you roasted them slowly, they gave off a gas that if you burned it was luminous. This was a remarkable development, but it actually took some engineers to make it practical. So here you see 3 engineers who actually turned this scientific curiosity into something that was a commercial and practical reality. Leave it to the engineers. William Murdoch, Samuel Clegg, and William Sugg. All of them worked in England, where the first developments of gas lighting were very prominent and very rapid. These 3 men were involved in the very earliest companies that were generating gas. Now, gas lighting works this way. If you look on your left, you have a crucible. Basically, it's a big oven where you roast coal. You collect the gas that comes off. You bubble it through water to take out the ammonia and the sulfur. You put it in a big expanding tank. The tank will feed pipes that finally carry it to its final destination, where it burns luminously. So the goal was to take something organic, cook it, capture the gas, and that becomes a commodity. Becomes a commodity because it burns luminously. And the whole point was that a gas that combusted with great luminosity. The gas companies actually needed to add things to make it burn that brightly. By 1850, gas lighting was the largest industry in the world. The world was more money involved in gas lighting than any other industry. And of course, the companies and the mechanisms to make the gas grew tremendously. 2 pictures of the great gas works. This is the later one, 1910, to supply the city of London. Gas lighting utterly changed urban lighting. Utterly. Lighting became a utility. It was no longer something you bought at a shop and carried around. It was something that you committed to by contract to an outfit that would sell it to you. Lighting became a civil engineering infrastructure. You had to dig pipelines through streets. You had to take pipes to houses. You had to have storage facilities. Gas lighting got coupled to the city and the density of population, which made it practical. And because there were several different companies making gases, photometry arose, commercial photometry. My gas burns brighter than yours. And the photometrist tells us that. We've had photometric reports for almost 200 years, right? And in many cases, people still don't understand them, right? Lighting becomes embedded in buildings. Very important thing. Lighting is now something that's mounted to the wall and not carried around. Made a change in architecture, too. If you look at lighting in the rural areas, you look at what was called at the time the use of illuminating oils. There are all different kinds of oils that people would burn in all different kinds of lamps. On the left, you see camphene lamps, something incredibly dangerous at a very low vapor pressure. It would blow up if you looked at it wrong, right? Because most of it was turpentine. The other lamp was lard at the other end of the volatility, right? Oil made from lard. I spent some time at the U.S. Patent Office. Here are the number of patents in the late 18th and 19th century taken out in the United States for illuminating oils and lighting equipment. And you see the clear evidence that people wanted a new lighting system because the number of patents went up by a factor of 10. The man who answered the call was a Canadian chemist, Abraham Gessner, and he discovered what he called kerosene in 1846. It was perfect as an illuminating oil. Low vapor pressure, so it wouldn't explode. You had to work at it to get it to explode. But it burned without smoke and very, very luminous. Kerosene utterly revolutionized rural lighting in Europe and America. Literally revolutionized it. Candles became obsolete because kerosene was cheaper. There was a young man, an engineer by avocation, but not by training, who designed some of the earliest and longest-lived kerosene burner implements. His name was Dietz. And we all probably owned something that was eventually made by his company and the company that came from it, called the Coleman Lantern Company, right? And we've all burned kerosene or something like kerosene, yes? Kerosene lamps were everywhere in the United States. They were everywhere in Europe. And as I say again, it utterly transformed what people did about lighting in rural areas. You could now afford safely lighting that you could carry around. But kerosene at that time was actually derived by cooking coal. But Gessner and other chemists knew that oil that you extracted from the ground, petroleum, Latin for rock oil, petroleum, could actually be distilled and you could get kerosene from it. So George Bissell, who has a history of drilling for salt water used in industry, said, let's drill a hole and get oil. And he commissioned Colonel Drake, and they were successful. And almost all kerosene began to be distilled from petroleum. So kerosene lighting has these characteristics and consequences. It began to be produced not from coal, but from oil. And oil seemed illimitable in its availability. Every time you poked a hole in Pennsylvania, oil came out, literally. And they hadn't even gotten to Texas yet. Right? It was safely used. The efficacy was incredibly high because it burned so luminously. Completely changed rural lighting, and it initiated the petroleum industry. The reason we have an oil industry in 19th century America is because of lighting. Oil became the biggest export of the United States to Europe because they wanted kerosene. So lighting had an incredibly important role in the economic foundation of modern industrial America. That's our lineage, right? Our forebears did that. Let me go back. Petroleum displaced candles. It's very interesting because there are a lot of economic consequences to that. Let me make it very clear. The people who were involved in making candles, the chemists, the factories, they had nothing more to do because they didn't know about kerosene. It was a whole different technology and a whole different set of people. There are always displaced people and industries when lighting technology changes. Always. I can find no exception to that. There are always people and industries that are displaced. Let us take heed. Right? We can actually see that happening. And of course, as I mentioned, there's a significant role that lighting had in the national economy. Right? I want to talk about the gas mantle because gas lighting lived a very long time, a century. It was the primary technology for lighting in cities in North America and in much of the developed world for more than a century. And that was the point of it, to make a gas that burned luminously. Along came an Austrian chemist, Karl Auer von Welsbach, who began to experiment with making substances that, if you heated them, would incandesce. They would be very luminous. And he found out that salts of thorium and cerium, in just the right proportions, would, if you heated them, incandesce brilliantly. So, the gas mantle was his invention. It was actually rather simple. It was a woven sock soaked in water in which you had dissolved these salts in just the right proportion. That was the key, right? Exactly the right proportion. And now you heated the sock with gas lighting. So the gas no longer had the job of being luminous itself. It needed merely to be hot, and it was good at that. So now the gas people could not have to add stuff anymore. The efficacy of gas mantle lighting was 5 times gas lighting. I'll say it again. Gas mantle lighting was 5 times as efficacious as ordinary gas lighting. It utterly changed, again, gas lighting. And so everywhere you had gas lighting fixtures that no longer had bare luminous flame, but actually had a small invisible flame, the kind of thing that the Bunsen burner does, right? To remove the hair on your underarm. Remember chemistry class, right? Would do that? Yeah. Gas mantle radically increased gas lighting efficacy. And it changed the needed property of a commodity. The gas no longer needed to burn luminously. It just had to be hot, that's all. The mantle was luminous. It was highly competitive with electricity. We'll talk about that more. It's a very radical issue. And because it was competitive with electricity, it long delayed the development of electric lighting. I will show you later on, there's economic evidence that electric lighting advent was delayed 35 years because of gas mantle lighting. It had a huge economic effect on electric lighting. Let's talk first about arc electric lighting. Very, very early, Humphrey Davy, 1808, showed that if you took electricity, you could draw an arc between 2 carbon rods. And the arc itself, electricity leaping through the air, ionizing the air, was incredibly luminous. But at that time, 1808, the only source of electricity were so-called voltaic piles, what we would call a battery. But Michael Faraday discovered electromagnetic induction. If you wave a magnet by a circuit of wire, you induce an electric current in the wire. And so it wasn't but 30 years when people were making very, very efficient electric generators to power an arc lighting like this. Now, one of the problems was the rod connected to the positive side of the generator burned more rapidly than the negative rod. So you had to move the 2 rods at different rates. So in order to do that, you used to have mechanisms like that. Pretty elaborate, to say the least. Right? Hardly practical. Nevertheless, American ingenuity, right? A young man from Cleveland, Ohio, all right, Charles Rush, discovered a very simple, elegant way to move the carbon rods, right, as they burn. It was a brilliant idea. He patented it. I'll say more about that later. And of course, he built a huge company. The first generating station in the United States for lighting was not Edison's, but it was Rush's. It was here in New York. He lit Broadway with his arc lights long before Edison was working on the incandescent. But the most brilliant idea of all was had by Pavel Yablokov, who was an electrical engineer, worked in Moscow, came to study electric lighting in Paris to solve the problem of a practical light. Yablokov said, well, if the positive rod burns faster than the negative, let's fix that in the following way. Let's take both rods and make them positive and alternately negative. Yablokov said, let's not use direct current, let's generate alternating current. Oh, brilliant. So now, both rods burn at the same rate. So now you could put the rods together like you see on the left, and the arc would burn down as both rods were consumed at the same rate. It burned sort of like a candle. So it was called Yablokov's candle. Utterly revolutionized electric lighting because it was the first electric lighting. Notice the date, 1876. In my collection of antiquarian materials, I have a pamphlet of his company for investors. And on the back of it is this picture. Yablokov got commissioned to light with his new lights the quay on the River Thames in London. And he was a brilliant ad man because he left the gas lights there. And the very bright lights you see are his lights. So of course everyone came along and said, "This is spectacular. We want this in our city." Of course. Look at it. It's wonderful. Right? So in order to judge, you must compare. And yet, within 5 years, his company was bankrupt. How could that be? Bad management, bad finances. It's a lesson to us all. Now, the other kind of electric lighting that we're probably more familiar with is incandescent lighting. The first one to tinker with this was a lawyer, William Groves, who was also an amateur natural philosopher. He was experimenting with a new kind of battery. Notice the dates, right? This is before Faraday's work. And he showed that you could take a platinum wire and make it incandesce if you took the oxygen. Two men began to chase this down in a very serious way. One was Joseph Swan, that you see on the left, and the other was the remarkably young Thomas Edison. These photos show the men as they were at the time that they were working on the incandescent electric lamp. This project was called Subdividing the Electric Light. If I took one of Pavel Yablikov's candles and put it in this room, you couldn't bear it. It was too bright. There was too much light. Hundreds of thousands of lumens. But it was perfect for streets, grand hotel lobbies. As a matter of fact, the Opera House in Paris was lighted with it. In December of 1879, both Joseph Swan and Thomas Edison had those prototype lamps the same month. Swan showed his lamp at a meeting of the British Association for the Advancement of Science in December of 1879 in Newcastle upon Tyne. Edison's lamp was shown on New Year's Eve at his Menlo Park facilities. Caused quite a stir. Here you see the first practical production electric lamps produced by Joseph Swan in England and Thomas Alva Edison in the United States. Swan's lamp had the better filament. It was actually cellulose that he had figured out how to squirt through a diamond die. Edison's was much more primitive. It was a sliver of bamboo that was carbonized, turned into charcoal. Right? But please notice the basis. Edison said, "I want something simple that would produce both the electrical connection and the mechanical support for the lamp." That idea did not occur to Joseph Swan. And so here you have a little detail that actually determined what the public thought was the most practical manifestation of the light source. The Edison screw base is almost unchanged from this lamp. That lamp is 1880. It was made almost the same way. Swan had imagined this trifoliated support with the lamp held by springs that had to be attached from the bottom. Imagine giving that to a contractor to install, right? Yeah. Now, as it turns out, Edison, his invention caused such a stir in the United States that money began to flood in amounts that we today find it very difficult to imagine. But all the people who had been making money in the steel industry, in the petroleum industry, in the railroad industry said, here is the next big thing, and I'm investing. And Edison had more money than he had people. It was a remarkable time. But it sounds familiar, doesn't it? Now, with electric lighting came the need to control it. It was a relatively small source, and it was very bright. And so you had the rise of lighting optics. The very first things that you and I would call a luminaire, or a light fixture, if you go to Walmart and ask, right? Andre Blondel was a great French illuminating engineer, probably one of the first illuminating engineers in the world. And he invented what we now call a halophane globe to control light. A more practical light source you see here. People saw the opportunity, people outside the lighting industry, saw the opportunity to spin steel and aluminum and make reflectors, to ride on the coattails of the new source. I bring this up because now there is a separate industry between the source and the lighting equipment. They're separate companies. They know each other very well, but they're separate companies. And it stayed that way for a very long time. With the advent of the discovery of how to electrolytically separate aluminum out of its naturally occurring ore, bauxite, aluminum became very inexpensive. It was a wonderful material for light fixtures because it wouldn't rust. And you could electroplate it and electrobrighten it. And you had something called LZAC. At the same time, and in the first instance in the lighting industry, arose the battle of intellectual property. Once Edison demonstrated his lamp, he applied for a patent. And the patent was granted in January of 1880. Here's the patent. He patented the idea of a closed globe with a fused base that held the supports for an incandescent filament. That was the patent. And it was granted. And Edison had a lock on the incandescent lamp. 10 years later, after long court battles, the District Court of the United States in New York upheld the patent. It was challenged. That patent was finally upheld in the United States Supreme Court in 1895. Now, the patent is interesting, and this issue of intellectual property is interesting, because if you look at the lighting that was used at the Chicago World's Fair in 1893, all the lamps were supplied by Westinghouse, and they were so-called bottle lamps. Westinghouse, because of patent law, was not allowed to use a fused seal on the bottom of his lamp. He actually had to have a ground stopper. Imagine how difficult it was to maintain that. But Edison had the patent. He who owns the intellectual property owns lighting. That's the lesson. And that's also playing out in our age right now. Right? Very clearly. So, electric lighting had profound consequences. We now see the advent of material science in lighting. Chemists got interested in lighting. Metallurgists got interested in lighting. Couldn't have light with a bamboo filament. What is that? Put some kind of metal in there. The only metal that makes any sense is tungsten. But the natural form of tungsten looks something like black baby powder. It's not a wire. It took a long time to make tungsten wire. You see some of these other issues, right? Electric lighting was safe, it was convenient. It brought about the notion of luminaires and optics, reflectors, and lighting control. Because electric lighting was electric, you could throw away some of the electricity with an old rheostat and dim it. And so electric lighting, among many of its cultural effects, utterly changed theater lighting. Right? Because you could change it. Lastly, let's look at fluorescent lighting. The man who invented the first practical fluorescent lamp was Edmund Germer, working in Berlin in the 1920s. He had been tinkering with low-pressure discharges of mercury in long tubes lined with fluorescent phosphors, naturally occurring phosphors, or phosphors. And by this time, General Electric was a gigantic company, and they were paying very close attention. They had already learned the lesson of intellectual property. The very first thing they did is buy all of Germer's patents. Right? They swept up all that stuff. And eventually, when General Electric learned how efficacious a fluorescent lamp could actually be, they assigned those two engineers to make a practical product. Right? George Inman and his partner, Thayer, worked for many years at General Electric, And they were the two men, two electrical engineers by training, lighting engineers by avocation, who actually made the first practical General Electric fluorescent lamps before the Second World War. They began working on this in 1935. I find it very interesting. There's a manuscript that they have that was written by Thayer that's still in existence at Nela Park in Cleveland, and I've read it. Thayer thought that they were working on a niche product. He thought this would be an interesting replacement for neon lights. General Electric had no idea that people would be interested in the fluorescent lamp. Why is that? It's big. All of a sudden, you've got to have a great big thing to hold it. You need a ballast to start it and to run it. General Electric thought, who wants that? Well, they were very surprised. On the left, you see the lamps that General Electric made before the Second World War. On the right, you see the lamps that they needed to provide the consumers in 1947. Fluorescent lighting went everywhere, literally everywhere. It was utterly unexpected. It changed luminaires. People began to wonder about ceilings. Modern ceiling technology is a result of the fluorescent lamp. Because now it occurred to everyone, we can put the luminaires up there. We can put air diffusers up there. We can hide all this junk up above this ceiling. And it changed buildings. The kinds of lines and styles that modern architecture wanted was a consequence of the fluorescent lamp. Once again, the fluorescent lamp brought a radical increase in the efficacy of electric lighting. Typical incandescent lamps at the time were about 10 lumens per watt. The first fluorescent lamp that General Electric sold produced 45 lumens per watt, 4.5 times the best incandescent lamp. People were astounded, and they wanted them. They bought them. Lamp size now is very large, which means luminaires became very large. And therefore, ultimately, they had a huge effect on architecture. We see the rise of prismatic optics, plastic optics, aluminum reflectors. Remember the parabolic truffer? Right? I mean, that was the response of technology to this new light source, right? And for the first time, there was significant auxiliary equipment required, ballasts and starters. So, let's take some stock now. There are economic consequences to each of these transformations that we've seen. These are disruptive technologies have produced tremendous economic consequences. The rise and fall of businesses, the coalescing of businesses. Without exception, this happens every time there's a radical change in lighting technology. There's no exception to this in the historical record, and I do not think we're going to see an exception this time. If you look at the Sweets catalog, before and after the Second World War, that is to say, before and after the advent of the fluorescent lamp, you see radically different companies. There's a tremendous change in consumer habit and expectations of sources. Everyone wanted high-efficacy lamps. And so the external effects were things like new luminaires, new optics, ceiling systems, changes in buildings, right? And so it seems that the past can be prelude. Now, this graph shows the development, circled in red, the General Electric Company. On the left, Westinghouse. This is from about 1875 to 1900. The yellow path that is passing down shows all the companies bought by the General Electric Company. So that by 1900, General Electric had subsumed lots of people who were in the lighting industry. On the left, you see George Westinghouse did the same thing. Until at 1900, there was essentially two sources of lights in the United States. General Electric and Westinghouse. And that was it. Because of intellectual property and because of the way businesses were put together. This issue of economics is very interesting. Here's a construction of the time-fixed cost of candle lighting. This is British pounds, this is a British study, British pounds per lumen hour from medieval times until the advent of electric lighting. Notice the huge swings in the cost of candles until you get to about 1840. That's when stearine and paraffin candles began to be manufactured on a uniform basis, and the price got lower and stabilized. I add as a complement the cost of whale oil light, because both in England and in the United States, whale oil was a very important illuminating oil. You go out and you poke a whale with a big stick, you kill it, you drag it home, you boil it down, and you get a lot of oil out of it, right? A lot of oil, yeah? And you sell that oil, and whale oil was important because it burned very clean, it was very luminous. So it was very much in advance like kerosene, only it was a natural product. It was hell on the whales though, right? You'll notice though that the cost of whale oil never stabilized. You go on a ship in the North Atlantic, well, here we go, right? Maybe we get whales, maybe we don't, right? Yeah. Maybe we get fed, maybe we don't. The cost of gaslight radically altered the cost of lighting because the cost of gaslight dropped precipitously. And I've seen this in all the technologies. On the left, you see dollars per 1,000 lumen hours. More interestingly, on the right, you see hours of work per 1,000 lumen hours to try and take the issue. In all cases, right, you see the tremendous drop in the cost of light. Every radical technology radically drops the cost of light. Without exception, the history always shows that eventually lighting becomes a new commodity. Without exception, in 250 years, there's never been exceptions again. Now, here's a chart that shows the use of candlelight and, in the latter part of the 19th century, kerosene light and gas lighting. Right? Now, this is in the United States, and you can see that once kerosene began to be produced, its use increased tremendously. Here's a curve of the cost of illuminating oils, including kerosene, right, over the course of the last half of the 19th century. And you see the typical tremendous drop in cost. It's almost a factor of 10 in the cost of illuminating oils. It's typical of what happens to these economic consequences to this radical change in the lighting. If you look at the use, naturally, if you make it cheaper, it gets used more. And so the more it got used, the more it was wanted, the less it could cost. And so you have the typical cycle where if you can get people to adopt it and want it, the cost drops and they want it even more. We see that all the time, right? The consumption of oil in the United States, this is, of course, before the automobile, rose very rapidly because oil was extracted from the ground and made kerosene. And everyone wanted kerosene oil. Now I want you to look at a very interesting chart. The green line shows, roughly, the cost of gas lighting. This is a British study. Pounds per million lumen hours. Look at the red line. That's the cost of kerosene lighting. You'll notice that it's very similar to the economic cost of gas lighting technology. Electric lighting doesn't have the same steep slope, and that's because it was being fought with by mantle gas lighting. And so the cost was higher, longer. So technology battles are economically expensive. That's an important thing for us to remember. by the time technology is being battled out, you and I are paying more. It's basically what that shows. I want to show you a couple things. If you look at the price of kerosene lighting, just after 1850, you see a radical shift in the cost of kerosene lighting. And that's because the United States was in the middle of a civil war. And oil production fell because the United States was the principal generator of oil for the world. And so the Brits ended up seeing a very sharp increase in the cost of kerosene. This is one of these external effects. War, politics ends up affecting lighting, right? The other thing I want to point out, there's the niche in the bit in the kerosene light caused by the American Civil War. The other thing I want to point out is when electric lighting finally achieved cost parity with gas lighting. In Britain, it was 1920. In the United States, it was only about 2 years earlier. Edison turned on his first practical electric lamp system in this city in 1882. And it wasn't until about 1918 before the cost of those two light sources were at parity. It took a long time to sort that out. So let's look at the stages of these things. What can we look at? In almost all cases, there's discovery and development involved in these technologies. Then there's deployment and commercialization that follows the development of these things. It makes sense, right? Now, with deployment and commercialization, you then finally have something that you offer the public. Part of the public resists. Competition arises for visionaries who see that you probably had a good idea and they want to get into the action. And finally, the public adopts the new lighting technology. Eventually, the new technology is ubiquitous. It's everywhere. And of course, one of the consequences of that is that lighting becomes a commodity. It becomes something with a very low profit margin. It becomes the technical equivalent of trying to sell paper towels. And when you go to the store to buy paper towels, you don't stand there for 10 minutes in front of the paper towel display. You just pick something that maybe you like. Should I get select a size or not? Do I want bunny rabbits printed on my paper towels? Now, in each of these cases, there are causes and opportunities that I've identified. Economics is a big issue. Technology, whether it's pursued or accidental, serendipitous, has always played a new role. Resources, either new, like oil, or now husbanded ones, like we're trying to do right now. But there are always effects that these disruptive technologies have. In all cases, the public eventually sees a diminishing cost of lighting. Without exception, that is always the effect that these technologies have. For business, it always has meant the demise of long-standing businesses and the arise of new ones. Without exception, every disruptive technology has produced economic disruption in the lighting industry. No exception. There are always new personnel come in, scientists, material scientists, people who were not involved in lighting before, all of a sudden are involved in lighting. Technology has, as each of these disruptive technologies has happened, had a major role. Architecture has changed in response to the lighting that we've given people. Let's look then at what might be some of the disruptive effects of LED lighting. Well, the first one that comes to mind are the thermal requirements. The LEDs appear to have promises of efficacy in life that we've never seen before. Luminous distribution from an LED is actually rather narrow. It can be changed a little bit, but it's not like one of those things there. Spectral composition can be changed. Control and interaction is now unbelievably flexible. And maybe there'll be an effect in architecture. I haven't seen that yet, but we might see it. So, the LED is the first light source that we want to bolt a refrigerator to, right? In order to keep it cool. Because if it gets hot, the output goes down, and it's no better than an incandescent lamp, right? So, there are thermal requirements that LEDs have that no other light source has ever presented. We have to deal with that. Promises of efficacy in life, well, they could last a very long time. They could. And the efficacy promises are startling, right? You can get relatively wide-band LEDs, wide-band, relatively white, in the lab that will produce 250 lumens per watt. What does that mean? What if you had light sources that only that had an efficacy of 250 lumens per watt? What does it mean if they live forever? What does it mean to the lighting industry if it's that efficacious and lasts that long? How often do you start changing lighting, if ever? What happens to the buildings? What happens to us? I don't know. But the technology is going to tell us. Optics has been an important part of luminaire design for 150 years. It's no longer the case. If you go to the Orient, you can buy breadboards of LED dyes. And if you go down the street, you can find someone who makes little plastic bubbles, refractors that fit over each LED. That'll give you a type 5. So you buy this thing with LED dyes, you slap that piece of plastic on it, and you have a roadway luminaire. What does that mean for us? Because the technology is ultimately very simple, almost anyone can reproduce it, and I think that's problematic. LEDs offer the ability to change the spectral composition of the light in spaces in a way that we've never had before. You go outside there and you see those wonderful things that our company sells, right? Changing colors as you go by. It's magic. It's tremendous. But it could have health consequences too. Control and interaction has a flexibility that is almost hard to imagine, right? Tremendously different, tremendously extensive. We don't yet know what LEDs are going to do to architecture. So far, I don't think LEDs have done anything to architecture, because even the company that I work for is busy attempting to put LEDs into good old ordinary luminaires, right? So that people have something to buy, right? There's been no radical change yet. We're still in a mimicry phase, putting a new source in an old piece of equipment. It's okay. Got to do that, because that's how you make do. So, what does it mean then if we are right in the middle of another radical change in lighting? Some people think that it's merely a matter of that source that we thought was going to be replaced by that source is actually going to be replaced by that one. That may be true for a while, but I suspect that the lessons of history are telling us that that is only the beginning. Many thanks for your attention. If you wish, I'm happy to answer some questions based on the work I've done in history. or some alternative view. Question in the back.
You skipped the whole high-density discharge technology?
Sorry?
You skipped the entire high-density discharge technology? HRD?
I did. I skipped HID because I thought the last disruptive technology was fluorescent lamps. I don't think HID was disruptive. Right? The way that I looked at it. When I looked at the historical record, it was very interesting, but it was actually more continuous than it was disruptive. Yeah. Good question, Steve. Other questions? Folks, we appreciate you joining us tonight. We hope you find these sessions useful and informative. If anyone wants a copy of this presentation, and I have my notes in it as well, so you don't have to remember it. If you leave your business card up here, I'll make sure that the people who help bring these things together, like Jess here, will get a copy of it too. It's about 18 megabytes, because it's got a lot of nice pictures in it, right? So I'll be prepared. But by all means, make sure we get your business card. I have to get a copy too. Thank you again very much.